thing we would like to see here is what happens when we have a inductive load. We would like to, when it comes to the RL load, we'll go to the library browser and the passive component, and we'll add a RLC branch, and this time we'll choose only the inductor L. And let me just set this to 100 micro. Alright, so now I'm going to add in series the resistor. Yeah, that would be a better arrangement. Alright, so now let me just run this program simulation, and you can view from here. It says that the derivative state at time is not finite. The simulation will stop. There is singularity in the solution. So by that it means that we need to fix the problem of simulation step time. This is the thing that's causing a problem. Alright, so one way is I can try a different step size. Let me just try 6. Okay, I'm just telling you about the possibilities. Okay, so you can see it's now working fine. Just double click to see the result here. Auto scale, and then the x-axis zoom. Okay, so one thing that's for sure that we can replace we can just get rid of this number if either we just type in INF, that's for infinity. So you can see that that's gone now. So let's have a try. Okay, it's not gonna simulate without it. And okay, so we are facing this problem, and one way is we can go to the model setting and let's switch back to the variable step size, to this trapezoidal one, and this tolerance we can set this to, let's say 1e-6. Now have a try. So here's the our simulation result, and what we are looking at here is the current through the load and the voltage across the load. But if you look at the waveform between these 2 points, this is something that's going to make difference. So for that I'm going to just make it, I'm just going to delete this guy and set this to RL. Okay, so now this is just a single component, and the voltage that I'm gonna get will represents the voltage across this complete RL set. Okay, just reiterate, and now I'll just try to add the current and the voltage across this RLC branch. Now let me run it again, and here is our waveform. Now the important thing here you need to look at is this little portion where the voltage across this RL is getting negative, and the reason behind this is that there is no other path except this one, and the inductor is going to delay the turn off of this diode. So if we run this program for a bigger value of L, then have a look at this. The time for the negative portion of the voltage is extending. Okay, so one way to keep track of it, I'll just remove this load current and just observe the voltage for different values of inductor. So one good strategy to demonstrate the effect of this inductance on the output voltage. We'll use different values of inductor here, and we'll see the output voltage. That is by output voltage I mean the voltage of this point with respect to this whole RL component. So one good way is to select this line and enable the log signals. What it does is it log the signals, and you can see the previous signals. I mean, for different value of L, you can see them together. So let me just confirm the first value here is 100 micro, and we'll just run this simulation. And we are not interested in this scope, rather we'll go to the data inspector. Okay, so this I'll just clear the archive, the previous simulation. So here is the multimeter 1 output. I'll get to here, and rather I'll go here and zoom in time. Okay, so this is the waveform when we have the 100 micro inductance. Now let's jump to 500 for instance, and run again. And here I'll just check this one, and also check this new one. I'll change the color so that I can view and fit to scale. Now I'll just try to zoom few cycles. Okay, so there is not much difference as you can see here. So we'll go for even another simulation. I'll use even a bigger value of, let's say, 1000 micro this time. Run again, go to data inspector. Again, I need to change the color. Let me set this to green, and have a look. Now the negative part is even for longer time, and I can even use another value of, let's say, 5000 micro. Let's just run it again. Go to the data inspector, and check the previous simulations. I want to see them all together, and let me use this color and auto scale. And now, so have a look that as the value of inductance, as we are raising the value of inductance, the negative portion is the time for the negative portion is increasing. So that's because of the inductance. I mean, that's because of the inductance, because there is no other path and the inductor has to release its energy in this very loop. And as long as the energy inside this inductor is released, only after that the diode turns off, and the negative portion is no more there. And because turning off the diode means that the output is then essentially zero. So this is how you can simulate. Let me just set it to 10,000. This is how you can simulate for different parameter. And now I have simulated this one. I'll just use another color, or to scale, and so have a look. So that's the effect of value of inductance on the output voltage, or the voltage across this RL branch.